Hi, everyone. Today we're going to be learning about section 7.1, which is being able to multiply and divide rational expressions. So, our learning objectives for this section are the following. We're going to be able to determine the values for which a rational expression is undefined, aka when your denominator is zero when dealing with fractions. Our second objective is being able to simplify rational expressions. Our third and fourth are being able to both multiply and divide rational expressions. And then our last one is sort of looking at it in function notation and function format, being able to multiply and divide rational functions. So let's jump into it. Let's do some warm-up problems dealing with dividing and multiplying fractions and also simplifying them. So our first example, you can clearly see that our numerator and our denominator has a greatest common factor. We can pull out a 15y from both terms. And so how many times does 15 go into 90? 15 goes into 96 times. And how many times does y go into y? Once. So our numerator is now 6. And then what about our denominator? 15 goes into 15 exactly one time, and y goes into y squared exactly once. So y squared divided by y is just y. 15 divided by 15 is just 1. So in simplest form, we get 6 over y as our final result. Second warm-up example, we want to multiply these two fractions. Again, when you're multiplying fractions, think about it as one giant fraction, where you're taking the product of the numerators and then you're taking the product of the denominators. But before you take the product, see if you can find some common factors to make your multiplication a little easier. For example, 7 works for both 14 and 35. If I did 14 divided by 7, I would get 2. And if I did 35 divided by 7, I would get 5. So this can simplify to 2, and this could simplify to 5. What about 6 and 15? Ooh, a common factor is 3. 6 divided by 3 gives you 2. And 15 divided by 3 gives you 5. So now we're just looking at the product of 2 and 2 for our numerator, which is 4, and the product of 5 and 5 in our denominator, which is 25. And we can't simplify this any further, so this is our final result. Could you have done it the harder way where you just multiply straight across your 14 times 6? That gives you, that's the same as 60 plus 24, which is 84. And then your denominator, your 15 times 35. Well, that's the same as 350 plus 175, which is 455.25. And then simplifying it from there. And so 84 and 525 share a factor of 3. 84 divided by 3 gives us 28. 525 divided by 3 gives us 175. And then both of these go into 7. 7 goes into 175 25 times. And 7 goes into 28 4. and you'll notice you'll get the same result, but a lot more tedious. So use your number sense, look for patterns, and things will be a lot more straightforward, both in math and in life. Okay, our third warm-up example, we have divide these two fractions. So when you divide by a fraction, what's the trick? Keep, change, flip. Keep the first fraction the same, change the division to multiplication, and then flip that last fraction. So now it's looking like 25 over 8. And then once again, look for common factors. Common factor between 12 and 8 is 4. How many times does 4 go into 12? It goes in 3 times. How many times does 4 go into 8? It goes in twice. And then common factor between 10 and 25 is 5. How many times does 5 go into 10? 2 times. How many times does 5 go into 25? 5 times. Multiply your new numbers. We have 3 and 5 in your numerator, which gives you 15. And then we have 2 and 2 in your denominator, which gives you 4. 15 over 4 is your final result. Put it into mixed fraction form, and you get 4 goes into 15 3 times, which gives you a remainder of 3. So 3 and 3/4. Either of these answers will yield you full credit. Right, so we completed our warm-up. Let's jump into our formal definition of a rational expression. So any rational expression can be written in the form of P over Q, where both P and Q are polynomials, which we've defined in earlier lessons. And something to really keep in mind is your Q value cannot be equal to 0, because if it is, it makes that fraction undefined and we're in sort of uncharted territories. Below, we have some examples of rational expressions. Whether they do not contain variables, still a rational expression. We're just dealing with a constant. Or we have some variables. Maybe we have a binomial in the numerator, or even a trinomial in the numerator. We're still dealing with a rational expression. Okay, and so this is our first objective that we're going to cover in this section. We have a notes section on that sort of undefined representation in rational expressions, aka if the denominator is 0. And this is important to know because it also really helps us in defining our domains of these types of functions when we end up getting to them later on. So if the denominator is 0, the rational expression is undefined. The numerator of a rational expression may be 0. There are no restrictions there, but not the denominator. So you really, really, really want to be on the lookout for that. I'll highlight. When we work with a numerical fraction, it's easy to avoid dividing by 0 because we can see the number in the denominator. In order to avoid dividing by 0 in a rational expression, we must not allow values of the variable that will make the denominator 0, aka helping us find our domain. So how do we do that? In order to find our domain, again, from a function perspective, we just simply set the denominator equal to 0 and solve the equation in order to evaluate these restrictions, in order to find our restricted values. So now knowing this, why don't we look at these 3 examples and figure out for what values make these rational expressions undefined? Let's not worry about the numerators. That's not our concern right now. We really just want to hone in on these denominators and set them equal to 0 to figure out what values make them 0. So in part A, we set 3c equal to 0. which tells us that c equals 0 makes our expression undefined. Therefore, our restriction is 0, which means c should not be equal to 0. Okay. Our second example, part B, we have 2b plus 5. Set that equal to 0. Let's utilize some inverse operations by subtracting both sides by 5. Now we're looking at 2b is equal to -5. Last step is let's divide both sides by 2, which means b is equal to -5/2, makes our expression undefined. Therefore, our b should not be equal to 5/2. It's not part of our domain if we were looking at this as a function and not an expression. Then our last scenario, we have this whole x squared plus 5x plus 6 set equal to 0, but lucky for us, we can utilize our handy-dandy factoring skills and factor that left-hand side. What are factor pairs of 6 that add up to 5? Ooh, 2 and 3. And now what values of x make this equal to 0? Well, we have x plus 2 set equal to 0. And then we have x plus 3 set equal to 0. Utilize your inverse operations. Should be a -2. And this is a -3. And so our two restrictions here are x is equal to -2 and x is equal to -3. These two values makes our expression not defined. It should be undefined. And again, it's both of them. And so what does this tell us? Therefore, our x values should not be equal to -3 or -2. Okay. These values should not be in our domain. Right, our next slide is another notes slide. We have a fraction is considered simplified if there are no common factors other than 1 in its numerator and denominator. Similarly, a simplified rational expression has no common factors other than 1 in its numerator and its denominator. So our simplified rational expression definition is it's considered simplified if there are no common factors in both the numerator and denominator. How to simplify a rational expression. These are the short steps in order to do so. You just want to be able to factor the numerator and denominator completely, and you do that by finding common factors between the terms or numbers that we're looking at. So knowing this, why don't we look at example 2 here? Once again, we can utilize our famous factoring techniques that we learned earlier throughout this course. Our numerator can be simplified into x plus 2 and x plus 3. And our denominator, let's use maybe green here, can be simplified into x plus 6 and x plus 2. And you'll notice that we have x plus 2 in both the numerator and denominator. So that can cancel out, which tells us our simplified fraction is just x plus 3 divided by x plus 6. And we're done. Let's look at another example together. And here, let's maybe first pull out some greatest common factors. In our numerator, we can pull out a 3 from each term. And when we do, we're left with a squared minus 4ab plus 4b squared. In the denominator, we can pull out a 6 from each term. And when we do, we're left with a squared minus 4b squared. And so that 3 divided by 6 can be simplified to 1/2. So we have 1/2. And then we have a squared minus 4ab plus 4b squared. So what are factor pairs of our 4b squared that add to negative 4ab? Well, factor pairs of 4 are 1 and 4 and 2 and 2. Probably going to look at the 2 and 2. And because the b is negative, it's probably going to be negative 2 and negative 2. And because there's this b squared, and we need to add up to negative 4b, should be negative 2b and negative 2b. And then we have our a, stays the same. So if you check that, that should work. I'll highlight this so you can really see it. And then that bottom is difference of squares, right? What's the square root of 4b squared? That's just 2b. So we can break this up into an a plus 2b and an a minus 2b. Would you look at that, we have some more cancelizations. A minus 2b in the numerator and an a minus 2b in the denominator. So our final simplified results, we have a minus 2b all over 2 in parentheses a plus 2b. And we are done. Okay. So let's move on to the next slide, where we have opposites in a rational expression. And this is dealing with if you have an a minus b versus a b minus a, we can factor out a negative from one of the expressions, and then we can actually end up simplifying that whole thing to just -1. And so that really, really helps us in certain circumstances, and we'll see this occur in a future example. Maybe let's highlight this. Okay. So in example 4, let's factor that numerator. Factor pairs of -32 that add to -4. We have x minus 8 and x plus 4 all over 64 minus x squared. Difference of squares, this is the same as 8 plus x and 8 minus x. And you'll notice that we have an x minus 8 here and an 8 minus x here. Well, why don't we factor out a negative in that bottom binomial? And when we do, if we pull out a negative value, we're now looking at -8 plus x. And negative 8 plus x is the same as, let's utilize our commutative property, x minus 8. So we can rewrite everything else to be exactly the same. Again, this is multiplication, it's not a minus. This too. So what does that tell us? Well, that x minus 8s cancel out. And so we're really left with x minus 4 in the numerator. That negative will move to the front, and 8 plus x is the same as x plus 8. So we can keep it like that. That will give you full credit, or if you wanted to bring that negative in the numerator, we could have negative x minus 4 all over x plus 8. Either of these would suffice. And we're done. Our objective 3, learning how to multiply rational expressions. Same as fractions, you're just dealing with variables at this point. You want to multiply the two numerators, multiply the two denominators, and then simply simplify. These are the formalized steps. Again, really being able to find those common factors so that you can simplify completely. So let's look at example 5. Let's factor out that first denominator. Factor pairs of 12 that add to negative 7, negative 4, and negative 3. 2x I'm going to keep as is. X squared minus 9, difference of squares, is the same as x plus 9, or sorry, not x plus 9, x plus 3, x minus 3. And then I'll keep the 6x squared as is. Now, 2x and 6x squared, well, 2x goes into 6x squared how many times? 3x times, and 2x goes into 2x 1 time. We have an x minus 3 in the denominator here and in the numerator up here, so we can cancel those out. So we're essentially just looking at x plus 3 all divided by 3x in parentheses x minus 4. And we have our simplified result. We're done. Let's do another example together. Color coding really comes in handy. Let's factor that first example, maybe using AC method off to the side. A times C gives you negative 9. Factor pairs of negative 9 that add up to negative 8. We have negative 9 and positive 1. And so we can really break this up into keep the first example or first term the same as well as the last. But break up that middle term into a minus 9a plus a 1a. We'll get back to that later. Now our denominator for that fraction, we have a difference of squares. So we can break that up into a plus 5, a minus 5. And then we can look at that second fraction. Factor out that numerator, factor pairs of 25 that add to 10, 5 and 5. So that can be broken up into a plus 5 in parentheses a plus 5. Let's look at that denominator. Another AC method we can put off to the side. Two times -5 is -10. B value is -14. What are factor pairs of -10 that add to -14? I do not think that is possible. Let's see. We have 1, 10, 2, and 5. And that is it. So it doesn't look like that is factorable, so why don't we just write it normally? And so now let's look at that purple example. Let's pull out a GCF, those first two terms. We can pull out a 3a. We're left with a minus 9. Second term, we can pull out a plus 1. Sorry, we're left with a minus 3. And then that second part can pull out a plus 1, and we're left with a minus 3. And we'll leave everything else. Or why don't we all put this under one fraction now? Okay. And so let's factor out that a minus 3. So we're looking at 3a plus 1 in parentheses a minus 3. Again, this was our purple, but we'll just get rid of all the colors now. A plus 5, a plus 5, all over a plus 5, a minus 5. And then we have this 2a squared minus 14a minus 5. So some cancelizations, a plus 5, a plus 5, and that is it. So our final result is 3a plus 1 in parentheses, a minus 3, a minus 5, all over, sorry, a plus 5, all over a minus 5, in parentheses 2a squared minus 14a minus 5. Little messy, but sometimes that is indeed the case. And we're good. All right. Our fourth objective, we have dividing rational expressions. So when you divide by a fraction, what's the trick? Keep, change, flip. Keep the first fraction the same. Change the operation from division to multiplication, and then flip that last fraction. So instead of looking at c over d, it's now d over c. And then you're back to the rules of multiplication. These are the formalized steps when dividing rational expressions, but let's put it into practice utilizing this first example. So we're going to just first put everything all under one fraction from a multiplication perspective. We're keeping that first fraction exactly the same, and then we're turning it into multiplication and flipping that second fraction. So now 6 is in the numerator, and now our p squared minus q squared is in the denominator. And now let's deal with some factoring. P squared minus Q squared is a difference of squares. We can break that up into P plus Q and P minus Q. And then we have that cubic function, our P cubed plus Q cubed, which what does this look like as an extension? This is the same as P plus Q in parentheses multiplied by our trinomial, which is P squared minus our PQ, and then plus Q squared. And if you're not convinced, you can always check. P times P squared is P cubed. P times negative PQ is a negative P squared Q. P times Q squared is a plus PQ squared. And then we have Q times P squared is plus P squared Q, which makes that cancel out. Q times negative PQ is a minus PQ squared, which makes that middle term also cancel out. And then finally we have Q times Q squared, which gives you that plus Q to the third. So that is correct. Which means, what can we do? We can replace the pink with pink. And then finally, we have, maybe I'll highlight that last thing in the denominator in orange. We can factor that out. We can first pull out a greatest common factor, right? We could pull out a 2. And when we do pull out a 2, we're left with P squared plus PQ plus Q squared. And is that factorable at all? Let's see. What are factor pairs of Q squared that add to Q? Yeah, this is not factorable. So is a prime trinomial. So we can leave it as is. What do you kind of notice here? Another thing that I want to sort of point out, it's good to have a really good knowledge of your sums of cubes and difference of cubes, because your P to the third minus Q to the third expands out into P minus Q in parentheses P squared plus PQ plus Q squared, which you'll notice is sort of part of that orange. And then we have a P minus Q over here. So what we can do is we can maybe keep the pink as P cubed plus Q cubed. And then we also see the 6 and the 2. 2 goes into 6 3 times, 2 goes into 2 once. And so if we keep that pink as just P to the third plus Q to the third, and then the green is our P to the third minus Q to the third. And this ends up looking like 3 in parentheses, p to the third plus q to the third, all over p to the third minus q to the third. And we can't forget about that additional p plus q. And we are done. So that completes example 7. We have another notes slide. Recall from use the language of algebra that is a complex fraction is a fraction that contains a fraction in the numerator, the denominator, or both. Really utilizing that whole keep, change, flip procedure. You want to remember a fraction bar means division. A lot of students make that common mistake. And a complex fraction is just another way of writing division of two fractions. Again, to divide by a fraction, here's a trick. Keep, change, flip. So let's look at example 8, where we are dividing a fraction by another fraction. So let's maybe look at this from the keep, change, flip perspective. So it looks a little easier. The main division sign is the one that I just highlighted in red. We're going to keep that numerator fraction exactly the same. We're going to change that red division sign into a multiplication dot. And then we're going to flip that bottom fraction so that x squared minus 5x plus 6 is the new numerator. And 2x squared minus 7x plus 3 is the new denominator. And now let's see if we can factor. For x minus 8, we can pull out a greatest common factor here. And when we do, let's pull out 2, and we're left with 2x minus 4. Now let's take a look at what I just highlighted in green. Factor pairs of 6 that add to negative 5. We have x minus 3 and x minus 2. Let's try and utilize our AC method for factoring 6x squared minus 7x plus 2. So our AC here is 6 times 2, which is 12. And our B is negative 7. What are factor pairs of 12 that add to negative 7? Well, we have negative 4 and negative 3. So we can break this up into 6x squared minus 4x minus 3x plus 2. Or it's better if we do the minus 3x first. The better greatest common factor, and then the minus 4x plus 2. And so when we do that, we pull out a greatest common factor of these first two terms, we end up getting 3x, and we're left with 2x minus 1. And then the last two terms, if we pull out a minus 2, we're left with 2x minus 1. And so now we can factor out that 2x minus 1. And so we're left with 3x minus 2 and that 2x minus 1. Coming along. Now let's use AC method to factor out that orange. So off to the side. Once again, have our A times C, which is 2 times 3, which is 6. And our B is -7 here. For factor pairs of 6 that add to -7, we have -6 and -1. So now let's break this up into, keep the first term the same and the last term the same. And then we have a minus 6x and a minus 1x. Pull out a greatest common factor. We'll pull out 2x from the first two terms. That way we're left with x minus 3. Let's pull out a 1 from the second part. And when we do, we're left with x minus 3. That way we can factor out that x minus 3 from each term. So we have x minus 3 and 2x minus 1. And again, we'll really zoom in on this part here. It's multiplication, so this is all really under one fraction. X minus 3 in a numerator, x minus 3 in the denominator. This is my favorite part. A lot of things cancel out. 2x minus 1 in the numerator, 2x minus 1 in the denominator. Anything else? You'll notice that this 2x minus 4, we can pull out another 2, and when we do, we're left with x minus 2. And x minus 2 in the numerator, x minus 2 in the denominator. So when we look at what's left, our numerator is just 3x minus 2 all over. We have 2 times 2 gives you 4. And that's it. Everything else canceled out beautifully. So crazy how this complex fraction just ends up simplifying to a binomial divided by a constant. Another little comment section. So if we have more than 2 rational expressions to work with, we still follow the same procedure. The first step will be to rewrite any division as multiplication by the reciprocal by utilizing our keep, change, flip. Then we factor, multiply, and fully simplify. So let's take a look at example 9 now. And so I'm going to put this all under one fraction, and I want to just be mindful that because of that division, I need to flip this numerator and denominator. As I'm putting it under one fraction, I'm going to try and pull out some greatest common factors to simplify along the way. I can pull out a 3, and I'm left with x minus 2. I can factor this into 2 binomials, our x plus 3, x minus 1. This is now in the numerator, and I'll pull out an 8. And this is all multiplication now. So now I have x plus 2. Now let's take a look at our denominator. I'm going to pull out a 4 here. So we have x minus 1. Factor this. Factor pairs of 10 that add to -3. Is that possible? Do not think it is, right? Because we have 5 and, oh no, it is. X minus 5 and x plus 2. Good. And then this is now in our denominator. Let's go ahead and pull out a 2. Now we're left with x plus 6. Great. Let's see if we can cancel out some stuff. Well, we have a 4 and a 2 in the denominator here, and 4 times 2 gives you 8, and we have an 8 in the numerator. So all of these can cancel out. And then we have, let's see, an x plus 2 in the numerator, x plus 2 in the denominator. Good. We have an x minus 1 in the numerator, x minus 1 in the denominator. Excellent. And I think that's it. So what are we left with? Our numerator, we have 3 in parentheses, x minus 2, x plus 3, all over. And then in our denominator, we have x minus 5, x plus 6. And we're done. All right. Keep on trucking. Our objective 5, which is our last objective of this section, is being able to multiply and divide rational functions. So it's just putting all of our rules and definitions together and now looking at it from function notation form. Also, just once again, keeping in mind that that denominator cannot be equal to 0 because if it does, it'll make everything undefined. And that's really where our sort of domain comes into place. What are our restrictions for this function? Those restrictions we need to exclude from our possible x values that make up our domain. All of the x values in a function, aka, is just another way of saying the domain of that rational function. Okay, and then these are the formalized step-by-step procedures in determining a domain of a rational function. So let's look at example 10, where we're asked to find the domain, aka first, let's find our restrictions so that we can exclude them. So how do we do that? We need to set this denominator equal to 0 to find those values that make the denominator undefined. Now 4x squared minus 16x minus 48, we can pull out a greatest common factor. Let's pull out a 4. And when we do, we're left with x squared minus 4x minus 12. And then we can factor this even further, factor pairs of negative 12 that add to negative 4 is simply negative 6 and positive 2. And so what does this tell us? Let's set x minus 6 equal to 0 and x plus 2 equal to 0. Inverse operations. Our two restrictions are x is equal to positive 6 or negative 2. Which tells us that x can't equal 6 or negative 2, because if it does, it makes our denominator 0, which makes it undefined. So therefore, what is our domain? Therefore, our domain must exclude these values. And so if we look at this on a number line perspective, we're excluding negative 2, and we're excluding positive 6, but all other values are free game. Which means in interval notation, we want to look at negative infinity up to -2. We're not including -2. We're including all values between -2 and 6, so we're going to create a union. And then we're also including all values from 6 to positive infinity. And so this represents our domain in interval notation. And there we go. We're done. Another little comment section. We have to multiply rational functions, we multiply the resulting rational expressions on the right side of the equation using the same techniques that we used to multiply rational expressions. So same exact process, we're just dealing with function notation in this next example. So example 11, we're given a function f of x and a function g of x, and we're asked to find the product of the two, aka we're multiplying them. So what do you have to do? You can just combine the numerators together by multiplication, taking the product of the two numerators and dividing and taking the product of the two denominators of the function. Now to simplify, I'm gonna pull out some greatest common factors and then use my specialing factoring tools. So with 2x minus 6, we can pull out a 2, and then we're left with x minus 3. With our x squared minus 25, this is difference of squares. So we're really looking at x plus 5, x minus 5. With our x squared minus 8x plus 15, what are factor pairs of 15 that add to -8? We have x minus 5 and x minus 3. And then finally, 2x plus 10, we can pull out a GCF of 2. And we're left with x plus 5. So let's see if any things cancel out from the numerator and denominator. We have an x minus 5 in the numerator as well as the denominator, so that cancels out. We have an x plus 5 in the numerator as well as the denominator, so that cancels out. We have an x minus 3 in the numerator as well as the denominator, so that cancels out. And would you look at that, we have a 2 in the numerator and a 2 in the denominator, so everything cancels out, and we're just left with our final results with a beautiful solution of 1. I love when it works out like that. Okay, we're almost near the end. We have our dividing rational functions. So to divide rational functions, we divide the resulting rational expressions on the right side of the equation using the same techniques that we did before when we were dividing rational expressions. So really utilizing and honing in on that whole keep, change, flip. We're going to put this all under one fraction. We're dividing. We have f of x divided by g of x. So that first fraction stays the same, 3x squared divided by our x squared minus 4x. But that second fraction is now going to be flipped. So we're going to have our x squared minus 7x plus 10 is now in our numerator, taking the product. And then our denominator is going to be 9x squared minus 45x. And now let's go ahead and use our knowledge of pulling out greatest common factors and utilizing our special factoring skills. So first off, x squared minus 7x plus 10, factor pairs of positive 10 that add to -7. We simply have x minus 5 and x minus 2. We're going to keep that 3x squared there. Then in the denominator, this x squared minus 4x, we can pull out an x, and then we're left with x minus 4. Now we have 9x squared minus 45x. Let's once again pull out a greatest common factor. We can pull out a 9x, and then we're left with x minus 5. And then let's see if we can cancel some stuff out. We have an x minus 5 in the numerator and the denominator. We have 3x squared in the numerator, and then we have a 9x squared in the denominator. So the x squareds can cancel out fully. And then 3 goes into 3 one time, but 3 goes into 9 3 times. So we're left with x minus 2 in the numerator, all divided by 3 in parentheses, x minus 4. And we're done. So that concludes our section 7.1. These are just some additional supplemental questions to really enforce your knowledge of this section. Highly recommend that you give these a shot on your own. And please let me know if you have any questions. Great work today, guys. Take care. I'll see you next time.